Before we get started, we need to answer one question. What is a derivative? Well, in calculus, the derivative is the slope of the tangent line to a graph. For instance, here's a graph, f of x, the point C that I've noted. The tangent to f at x equals c would look like this. In essence, a tangent line is just a line that touches the graph once at that point, sort of like a pencil resting there. Now, a function can have all sorts of different derivatives because, as you progress along a function, you can have all sorts of different tangent lines. Watch as the dot, which represents the x value, travels along the function, and how the tangent line changes as the dot moves. We need to figure out a way to determine exactly what the slope of that tangent line is, and we do that using something called the difference quotient. In this section, I'm going to show you exactly where the difference quotient comes from. Here's a graph called f, with a point on it labeled x. My goal will be to find the slope of the tangent line to f at that point. First things first, the coordinates of this point are x, comma f of x. Now, here's how I get my formula. I'm going to move a small distance to the right of x, and I'm going to call this small distance delta x. It's mathematical language for the change in x. Therefore, this new location is the total distance of x plus delta x from the origin. And this new point has coordinates x plus delta x, comma, f of x plus delta x. Now, if I draw the line that connects these 2 points in red, it's called a secant line. It's not exactly like the tangent line we're looking for that I'm showing in blue, but at least it's a start. I'm going to go ahead and try to find the slope of this secant line. And to do that, I'll use the old formula from algebra, where slope is equal to y2 minus y1 divided by x2 minus x1. And I'll get the slope is f of x plus delta x minus f of x, all divided by the quantity x plus delta x minus x. And if I subtract those x's in the denominator, I get this. Now remember, this is the slope of the secant line, not the tangent line, so I'm not done yet. I need to find a line which is closer to the tangent line than this one.
This is something you need to know, write down, or something to that effect, and that this is the formula for the slope of the secant line to the point you're looking to find. All right? Slope of the secant line, right there.
Let's look at that graph again. What happens if I were to make delta x smaller? In other words, my second point will be closer to x than it was before. Now, if I draw the secant line connecting my original point to my new point, which is slightly closer, I will get a secant line which looks more like the tangent line than the previous one did. It's getting closer to it. In fact, the smaller delta x is, the closer this secant line will be to the tangent line. Watch on this animation as the delta x goes from really big to really small. The red secant line comes closer and closer to the blue tangent line. We want delta x to be as small as possible. So therefore I need to make a small adjustment to my secant slope. Remember, that was f of x plus delta x minus f of x all over delta x. But we want to specifically say that that delta x needs to be as small as possible so those lines basically overlap. And to do that, we'll use a limit. All we do is add in the limit as delta x goes to 0. In other words, I want delta x to become so small it's almost 0. It can't be 0 because then I would have 0 in the denominator fraction. That's why I have to use a limit. And I say, get that delta x as small as possible. This is the difference quotient. It is the mathematical definition of the derivative.
And if you notice, the difference between the slope of the secant line and the slope of the tangent line, the only difference between the two formulas is the limit out in front. So as you see here, the definition of the derivative is exactly what was on there. The limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x. Now this derivative can have a few different notations. dy over dx. It could have y prime, f of x prime. It could have d sub x of y. That one's not highlighted because You don't see that one very often. The ones that are highlighted you see the most, and the derivative of f of x with respect to x. Now I'd like to show you analytically how to do a couple of these problems. So here is an example. Find the slope of the graph at a... So we're going to use the definition of the derivative. We are not, and I know from maybe physics, you might remember something like a power rule. Well, we don't use that here. We have to use the definition because somewhere along the line, maybe in an AP exam free response question, it might say illustrate by using definition. So you need to practice it at least once or twice before you can go into other shortcuts. So we're going to look at the definition. Limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. So that is the definition that you saw from the first part. Now, what I'm going to do is what you did in algebra, is everywhere I see an x, I'm going to replace it with x plus delta x here, and this is going to be the original. So it'll turn out to look like this. The limit as delta x approaches 0 of 2x plus delta x's minus 3, then minus, and then the original function, which is 2x minus 3. Notice I put some grouping symbols like brackets in for the original, and you'll see why, over delta x. Now I'd like to do a little algebra here. I'd like to say the limit as delta x goes to 0. Right now I haven't done the limit yet, so we carry the limit all the way through. And we're going to get 2x minus 2 delta x's minus 3 minus 2x plus 3, because all those signs will change, and then all over delta x. Well, something interesting should happen. The 2x's go out, the 3's go out. So I'm just left with the limit as delta x approaches 0 of 2 delta x's over delta x. Well, I can cancel out the delta x's, so really I'd be looking at the limit as delta x approaches 0 of 2. Well, that is just plain old 2. And it wanted to know, whoa, we got our slope here. We got our slope, and at this point, 2, 1, it's 2. You'll see in the next example that when they ask you at a different point and you get if you get an expression for an answer, you have to plug something in. So let's do that. Are there any questions? Yes. No, I'm just kidding. I can't see you. All right. Follow my algebra. Very easy algebra example here. Found out the slope is 2. Now we go on to this one. Find the slope of the graph of f of x equals x squared plus 1 at 2 points. All right. Well, we're gonna wind up looking at the slope first. So we're gonna use that definition. The limit. I'm not gonna write the definition out again. You have it maybe about 35 seconds before. The limit as delta x approaches 0 of the function. So it's going to be x plus delta x quantity squared plus 1. That's the f of x plus delta x minus the original. And I know you say, well, why is he using the grouping symbols? Can't I just do that? Yes. If you can just change the signs immediately, you're done. All right? So you can do it quickly. I'm doing it for all levels here. All right? For the people that I've seen this for the first time and people that are pros. All right, algebra man. Algebra man. Let's square that up. We're going to get something that looks like this, I hope. Help me out. If I'm wrong, if I've done something wrong, you're going to have to scream through the TV. You're going to have to scream through your phone or wherever you're watching this to help me out here, all right? Because I definitely need lots of help. And it's going to be minus x squared minus 1. I know, sometimes I make it sound like I'm not a genius, but you'll come to find that I probably am a genius. All right, let's combine some like terms. Gone, you're gone, you're gone. That's a good sign, because the last time, that's what happened. We got rid of some of those terms that had the non-delta x terms. Doesn't always happen, but in these examples it did. So I'm now left with the limit as delta x approaches 0, and I'm just going to factor a delta x out up front. Okay, on top, I get a delta x gone. I was leaning on my thing. Don't want you to think I'm bored or anything. Plus delta x. So I just factored out a nice delta x from the numerator, and now I get to cancel. Now I'll give you a different color like blue. I'll apply the limit. This becomes 0, and our slope is 2x. Well, now it's an expression. Before it was just 2. Now we have an x involved. And if you remember from the original problem that we wanted it at 0, 1 and -1, 2. So at 0, 1, what we're going to do is, remember, this is the x, this is the y. I'm going to plug in 0 for x. So at 0, 1, the slope is 2 times 0, which is 0. The y value doesn't matter. The y value doesn't matter. Unless you had a y in there. If you had a y in there, then of course we'd use it. The second point that it asked me to do, I have to scroll up because I have a short-term memory problem. -1, 2. Good thing I'm not getting tested on this. I'm just kidding. I would do pretty well. 2 times -1. Now at that point, it is -2. And just like the video stated, at different points, there's different slopes. Same thing here. From the other example, it didn't matter. The slope was always 2. This one, it changed. We'll do lots tomorrow.